Morning or afternoon or evening. Happy video notes 3.3. Here are the objectives for this slideshow. And here are the pages in your book. There's not that many pages, but read them. There's some good diagrams to show you what the explanations are. So we talked about polarity when we talked about bonds. Polarity means ended. Polar bonds, when you look at part of a molecule to see if the bonds are polar, you subtract their electronegativities, and then we did the cutoff point 0.4 or less was nonpolar, covalent, 0.5 to 1.9 was polar covalent bonds, and then 2 or higher was ionic. Okay, so if you have a polar bond, you could put this arrow on it, and this is the negative side, and this is the positive side. You could also use these symbols for partials. Now, when we're talking about bonds, we just check the two atoms in the bonds. But when we talk about molecules, we have to look at all of the bonds in the molecule and the shape. Okay. For instance, this bond is polar, so we could put an arrow on it. This bond is polar, so we could put an arrow on it. This molecule is shaped at an angle because those two lone pairs spread out. Everything spreads out. And since this top of the molecule is kind of negative and the bottom's kind of positive, this is a polar molecule with polar bonds. Okay, so the molecule is the whole thing. The bonds are just part. So here's what you need to know. In order to have a polar molecule, you have to have polar bonds in the molecule. You need a shape where that polarity of bonds does not cancel out. It makes a lopsided electron cloud distribution. To have nonpolar molecules, if you have no polar bonds in the molecule, automatically it's nonpolar. If you have polar bonds and they cancel out, then it's also nonpolar. So is the molecule polar? Well, let's look. Polar molecule if the shape and the bonds don't cancel. So over here you got extra electron density. Over here you got less electron density. So if you saw the cloud around this whole molecule, you have more electron density up here, so it's polar. In this molecule, it's tetrahedral, all right? And you have 3 bonds with no polarity, but 1 bond with polarity, so 1 dipole arrow in the molecule, so it's going to be polar because there's going to be more electron density here than over here. Same thing with that molecule. Look at these ones, though. This is a polar bond, another polar bond, but because the electron density is all around the outside, evenly distributed around the outside of the molecule, it's nonpolar. Okay. Same with this one. There are 4 polar bonds in the molecule, but then the whole molecule around the outside of the shape, nonpolar. Okay, same thing here. 1 bond that's polar means polar molecule. 1 bond that's polar means polar molecule and polar bond. 3 polar bonds that point to the top of a pyramid, it's going to be polar. Here we have 3 polar bonds, but this time they point to the sides of a triangle, trigonal planar. So that is nonpolar molecule, even though it has polar bonds. Here again, we have polar bonds, but they point to the corners of a tetrahedral. All right, we got the corners of a tetrahedral. And so it's a nonpolar molecule because those polar bonds cancel out. Same with carbon dioxide. All right, so here's the main idea. Molecules will be polar if the polar bonds don't cancel each other out and there's an uneven distribution of electron cloud in the molecule. That's a polar molecule. If the polarity of the bonds cancels out and there's an even distribution of electron cloud, you get a nonpolar molecule. Or if you have no polar bonds in the molecule, done, nonpolar molecule. Okay, here are 4 molecules. The blue represents positive charge, sort of, all right? But you can see positive, 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 positive. All around the outside is positive, so this is non-polar molecule. All right, so these are called electrostatic potential maps. Now, over here we have the red, so that's kind of negative. Down at this side of the molecule, we have kind of positive, right? And so you can see that this molecule, because of its shape, is polar. So it has polar bonds, and it's a polar molecule. Let's look at this one, H2O. So we got kind of positive down here, kind of negative up there. Okay, the shape of the molecule is a V. It's a polar molecule. Check out this one, HF. Right? Over here is the negative charge. Over here is the positive charge. Definitely polar because this side of the molecule is kind of negative. That's kind of okay. A bond is polar if the difference in electronegativity is big. The difference in electronegativity is big. So, a bond is only is 1 output 0.5 to 1.9. Okay. A molecule is polar if the bond is polar and the shape doesn't cancel that polarity. So, here are a bunch of molecules to decide if they're polar or nonpolar. So step 1, check the bonds. Right? This is a polar bond. That's a polar bond. How do I get? I subtract C and O. Right? But then if I check the shape, I see it's linear and those bonds cancel, so it's a nonpolar molecule. All right, let's look at this one. Check the bond between N and H. You get a polarity, so we can draw an arrow. So this is like 2.1, that's like 3.0. So what's the diff? 0.9. That means polar bond. So then I draw the arrows on it, and I find out that this shape is trigonal-pyramidal. Trigonal-pyramidal. Right? And so then the top of this molecule is kind of negative. The bottom of the triangle pyramid is kind of positive. So this is a polar molecule. Polar bonds within a polar molecule. Okay. What about this one? Okay, so this is one area, one atom in the middle, 1, 2, 3 areas of electrons. So it's trigonal planar. Right. And then if you check the polarity of the bonds, they're all going to go this way. But the fact that it's a flat triangle, it's a nonpolar molecule. Okay. That's what I mean by bonds canceling out. They're all pointing to the corner of the triangle. So all around the outside is the same charge, and there's no opposites. Okay, there's a couple more on the page, but we're going to let you practice those in class. Polar molecules love water. Why? Because water's polar. So things that are polar mix together. So like dissolves like is a concept we use to explain which things mix. Okay, so polar dissolves polar. And then nonpolar dissolves or mixes with nonpolar. So let's see what happens when we mix hexane and water. Uh-oh, we get 2 layers. Hexane is nonpolar as a molecule, and water is polar. Polar. Here we go with the water. Polar. Okay. Sugar has a lot of polar bonds, a lot of OHs. So you got a kind of negative charge there, kind of negative there, kind of negative there, kind of positive. So you put sugar in the water and they mix. Sugar's polar. Water's polar. Water's polar. They mix. Sugar's polar. Water's polar. They mix. Woo-hoo. All right, so we're going to talk about forces now, and we need to define 2 prefixes, inter and intra. Inter means between, like the interstate goes between state. It's like holding hands between 2 people, right? Intra means within. Intramurals are within the school, kind of like your bones are holding you together. Okay, within you, your bones hold you together. Within the country, the interstate holds the states together, but the states are still separate. Okay. Covalent bonds are intramolecular. They're within a molecule to make the atoms stay together by sharing electrons. Intermolecular forces are between different molecules. So the molecule's already made, it's being held together by covalent bonds, but then 2 molecules are attracted to each other by intermolecular forces. Inter is weaker by 10 times, a factor of 10 or so. So it takes 10 times the energy to break a bond between H and O as it does to overcome the force holding 2 water molecules together. Okay, so this is intermolecular between these 2 molecules. This is intramolecular, and that's a covalent bond. Covalent bond. What's stronger? Much stronger. Much. Okay, write it 10 times stronger. Okay. But these intermolecular forces are what make water a liquid at room temperature. Okay. Intermolecular are usually weaker than intra, and what determines intermolecular is molecular polarity. So you could have nonpolar molecules, polar molecules, or superpolar molecules. All right, so write these down. These are the 3 types of forces that we describe as intermolecular. All right, London dispersion forces. These are only kind of force between, I just write out between nonpolar molecules. So if you have a nonpolar molecule, it'll have an attraction to another nonpolar molecule. It'll be called a London dispersion force. If you have a polar molecule, polar to polar, they'll be attracted by the opposite charges. Okay. If you have a molecule with hydrogen bonded to nitrogen, oxygen, or fluorine, okay, that's a special characteristic. It's going to attract one molecule really strongly to another molecule, and it's much stronger than those other 2 forces. So, what's the first one? Dispersion, London dispersion forces. And it happens because of electrons. All atoms have electrons, all molecules have electrons, and electrons are always moving. And then in 1 second, you could have more electrons on this side of the molecule than that side. And so it's uneven distribution temporarily. We call it temporary dipole. Okay. And the more atoms you have, the stronger the force. Dipole is a permanent dipole, means permanent positive and negative charge. So this is the negative side, that's the positive side, it's always there. So once you have that permanent charge, they'll be attracted to other molecules more strongly. Hydrogen bonds is when you have an O, an A, N, O, or F bonded to H in your molecule, then it's a very polar bond, and then it's going to make a very polar molecule. Very polar molecule. And so if you have very polar molecules, they have stronger attractions between them. Okay, so rank them. London dispersion forces are the weakest kind of intermolecular. Dipole, medium. Hydrogen bonding, strongest linked H bond. Okay, but that was just for intermolecular forces. Remember that a covalent bond is stronger than all of those. Okay, so what happens because of these forces? Well, you got viscosity, resistance to flow. High intermolecular force means high viscosity. Okay, state of matter. Solid is most attracted, liquid next. So high intermolecular force, maybe solid. Maybe solid. Okay. Volatility, ability to turn into gas easily. Okay. Weak attractions. So high intermolecular force means not so volatile. Surface tension is when you have a liquid and the molecules are pulling in towards each other. Okay. So high intermolecular forces, strong surface tension. Right, so now we can start explaining all these cool things that we noticed about matter. Okay, hydrogen bonding is what makes water so amazing. So some of these properties are caused by hydrogen bonding. And yeah, see the water droplet, how do you break the tension? Okay, difference between the types of bonding again, or bonding forces again. Right? Intra is within, like your bones, strongest. Right? And here are the 3 kinds. This is the one we're focusing on in this chapter. Inter is between, weaker than those. Okay, so I'll put stronger than those. Intra is stronger than inter. Here are the 3 kinds that you have to know. Okay? All right, here's the review. Woohoo, we made it to the end. All right. Also, I asked you to read these pages in the book, and if you have a dipole, then you've got to have a moment. Peace out. Here's our objectives. We'll look at those later.